I'm gonna go 2. Okay, cool. All right, so let's go ahead and just finish up talking about the areas of the brain. There are 4 specific areas that I want you to be aware of when looking at the cerebral cortex. Okay, you have 2 areas within the frontal lobe, an area within the parietal lobe, and then an area within the temporal lobe. Okay, so let's talk about the 2 strips. Okay, so you have this sulcus here that separates the frontal from the parietal. And on either side of that sulcus, you have a strip of cerebral cortex that is dedicated to a very specific function. Okay, the strip that is in the frontal lobe. Okay, so this strip right here is called the what? The what? What do you guys think? This is known as the motor. This is known as the motor cortex. This is where most of the motor control for the brain comes from, okay? So motor information comes out of here. This is the motor cortex, the primary motor cortex, okay? Then you have the sulcus, and then this strip of cortex in the parietal lobe is known as the sensory. This is the primary sensory cortex. All right. You guys cool with that? So I've got the motor cortex, which is the back part of the frontal lobe, and then the sensory cortex, which is the front part of the parietal lobe. You guys cool with that? And then I have 2 areas that are important in language processing and being able to articulate. I have an area right here in the bottom of the frontal lobe next to the temporal lobe, right on top of the temporal lobe. And that is something known as Broca's area. Broca's area. Okay, that's Broca's area there. There is an area here in the temporal lobe, kind of toward the back of the temporal lobe, just underneath the parietal lobe. This is known as Wernicke's area. This is known as Wernicke's area. These are both involved in language processing, in language, okay? Damage to these areas results in aphasia. You guys remember aphasia, right? What aphasia is? Yes, it is an inability to articulate language. Now, damage to one area causes what's known as a receptive aphasia. Receptive aphasia is receiving language and understanding it. Okay? So, do I understand the input, the language coming in? That is receptive aphasia. Inability to receive the information. And then there's something called expressive aphasia, which is an inability to express the language. Okay?
Expressive?
Expressive. So you have receptive aphasia and expressive aphasia. Can I receive that information and can I express it? Okay? Now you guys have all heard of something known as Wernicke's encephalopathy, right?
Yes.
And we know that this can sometimes occur in patients who are very malnourished, like alcoholics, brittle diabetics, those kinds of patients. And when we give them dextrose, if they're really hypoglycemic, sometimes that can cause problems because they're thiamine depleted. And what happens in those patients is that causes a encephalopathy. Encephalopathy is just a word that means dysfunction of the brain, right? And that causes damage to Wernicke's area. And that causes something known as Wernicke's encephalopathy, which you guys should have already talked about as intermediates, right? Wernicke's encephalopathy is damage to Wernicke's area, okay? And this causes an expressive aphasia. These patients are not able to express. They don't have the ability to express it. because the ability to express language is a different area of the brain than the ability to understand. So they understand you just fine. You can talk to them, and they understand what you're saying just fine, but they do not have the ability to express.
Is there any way or like any other science that you could use to differentiate Wernicke's and Cephalopolyp from just being like drunk and not being able to?
No, it takes hours for Wernicke's to develop. Okay, you give somebody dextrose and he's not like instantly going to put them in
Oh, so
Wernicke's.
it's after you give them dextrose.
Yeah, you have a little time, so it's not like just some instant, oh, you just fried their Wernicke's area, because nothing like that. But they do need within a reasonable amount of time of getting the dextrose, you do need to get some binding on board.
So I saw in some, I don't know if it's in ours, but I saw in some of my research somewhere that you should give thiamine definitely before you give dextrose. So would that be like?
Nothing that I've seen, no. No, nothing that I've seen. Yeah, generally you have a little bit of time. Yeah, generally you have a little bit of time to, because you guys don't carry thiamine out in the field,
Yeah,
right? Oh, do you?
Yeah.
Oh, give it. Generally you only carry a couple 100 milligrams though, right? You really need to give a lot more than that.
And it's on back order, so we've run out.
Yeah. What you do need to do is if you give dextrose, you need to give report, right? In your report, you need to say, hey, look, this patient has a history of being malnourished, right? I think there might be a problem with chronic malnourishment. You probably need to get some finding on board, right? And generally, part of the banana bag, right, that we give people that we suspect being malnourished, quote unquote banana bags, contains at least a few hundred milligrams of thiamine. Okay, you guys good with that? So you guys good with your motor? So if I damage the motor cortex, okay, if I have a stroke and there's damage to the motor cortex, that's going to damage my ability to move, right? It's going to create an inability to move. If I damage the sensory cortex, that is going to damage my ability to process sensory information. All right, you guys cool with that? Damage to Broca's area is going to cause a receptive aphasia. Damage to Wernicke's is going to cause an expressive aphasia. You guys good with that? Make sense? All right, cool. All right, so let's move on. Let's now move on to how do I get blood into the brain? Okay, how do I get blood in the brain? That's kind of an important thing, right? Your neurons are highly aerobic. Okay, they rely heavily upon aerobic metabolism. Okay, they do not tolerate anaerobic conditions at all, right? They're not like muscle cells at all. So you need constant circulation. So the way that I look at circulation in the brain is you have an anterior source of circulation and a posterior source of circulation. Okay? You guys go with that? Anterior and posterior. Now, there is a backup mechanism if your anterior or your posterior fails. Okay? There's a backup mechanism. There's a mechanism that allows that if the posterior fails, okay, there's a way for anterior circulation to get to the posterior, okay? And that backup is what's known as the circle of Willis, okay? Yeah. And you know what? That's interesting you mentioned that because he died of a head injury.
Yeah, he did.
Right? So there you go. All right. So we need to go back to cardiology. And I'm sure you guys are going to be able to tell me what these structures are.
Absolutely.
Yeah, I'm sure you will. Okay, so what are the three major vessels that branch off of the aortic arch?
Left and right.
What's this one here?
The right
The right one. The right one. Say it again. You're so close, I shouldn't say anything.
I said clavicular somewhere in there, and I also said artery.
This is the right subclavian. Subclavian.
And then the break is
So the right subclavian is here. Okay, it's the first one that comes off the aortic arch. The last one that comes off the aortic arch is the left subclavian. All right. And then what? The one in the middle here is the brachiocephalic, right? Right. So this is the brachiocephalic.
It's the left, right?
I'm just gonna call it brachiocephalic.
Okay.
All right. That means it goes to the
Head.
brachial and hip. Guys cool with that? Okay, cool. So the right and left subclavians, we're going to look at those. From the right and left subclavians, there are two major arteries that, well, a artery that comes off of the right and an artery that comes off the left.
Anterior
Okay.
cerebral artery.
These are known as, let's say that again.
Anterior cerebral.
No, these are known as, this is at the aortic arch here. These are known as the left and right vertebral arteries. The vertebral. So this is the left vertebral, and I'll talk about why we call it the left vertebral and why we call it the right vertebral. The vertebral arteries, these guys here, see how I drew them behind these arteries here?
Mm-hmm.
These guys here, the vertebral arteries, come off of the subclavian, and they are the posterior circulation. Are you guys okay with that? Posterior. So the right and left vertebral arteries come off the subclavian. So here's my patient, right? Here are the clavicles, the subclavian comes up. And the vertebral arteries, do you guys see the cervical vertebrae here?
Mm-hmm.
And if you look at the cervical vertebrae, there's something special about the cervical vertebrae as opposed to, say, the thoracic vertebrae.
Oh, it has.
There is a little hole in each of these vertebrae, a forama. And that little hole is where the vertebral artery comes up into the brain. So the vertebral artery comes off the subclavian, goes into the cervical spine, and then follows the right side, the left follows the left side, and goes up through those holes in the cervical vertebrae until it gets into the base of the brain. You guys good with that?
Mm-hmm.
And you can see that's posterior, right? You guys see that?
Mm-hmm.
Okay, you guys cool with that?
Mm-hmm.
That's the posterior blood supply to the brain, the vertebral arteries. Now, there are two other vessels, okay? There is this vessel here on the right that comes off of the subclavian. That is known as the common carotid, the right common carotid. And the left common carotid comes off of the brachiocephalic here. So I've got the common carotids, we'll call them. And the carotid actually branches into the internal carotid and the external carotid. You guys okay with that? So the common carotid branches into the internal and external. The external carotid, which is the one that we're most familiar with, the external carotid artery is what supplies all the stuff outside of the brain with blood. So it supplies the face, the scalp, the eyes, all of this external stuff. You guys okay with that? The internal carotid is what shoots up, okay, shoots up on the anterior part. Okay, so the vertebral arteries are back here. The internal carotid arteries shoot up, okay, into the base of the brain. You guys cool with that? So the vertebral arteries enter, okay, at the back of the brainstem, behind the brainstem, if you will, and the internal carotids, which are these here. So I've got the left internal carotid and the right internal carotid. Okay, they come up here in front of the brainstem. You guys okay with that? And so what I've done is I've drawn the brain like this. You guys go with that?
Yeah.
So you were looking at the posterior surface of the brain. So you see this little thing here?
Mm-hmm.
This is the brainstem shooting out at you. You guys okay with that? This is the brainstem shooting out at you. So I have my vertebral arteries are back here. So the vertebral arteries are back here on the back of the brainstem. Okay? And what I'm going to do is where the vertebral arteries come in and where the internal carotids come in, this whole area here, I'm going to enlarge and make it this drawing right here. Are you guys cool with that?
Yes.
Okay. So here is my left vertebral and my right vertebral artery. You see that there? They're coming in, and you see how I draw the arrows that the blood is coming in?
Yes.
Okay. And these large holes here are my internal carotid arteries. So blood is coming here. Are you guys good with that? So here, here. So this is posterior. And this is more anterior. You guys okay with that?
Mm-hmm.
Posterior, anterior. And then the brainstem is kind of coming out of the board at you like this. You guys good with that? All right. Can you kind of see that or
Yeah,
visualize
yeah.
that? All right. So what happens is I'm gonna start posterior first. So blood comes in posterior through the vertebral arteries, and then the vertebral arteries branch into they branch into the posterior inferior cerebellar. Don't memorize these, okay? They branch out into the posterior inferior cerebellar, the anterior inferior cerebellar. So the blood that comes off of these primarily goes to the cerebellum, right? Supplies the cerebellum with blood. And then what happens is there is a large artery that goes up, okay, up the brainstem. So it makes its way right up the front of the brainstem, okay, up this way toward the anterior part of the brain, right up the middle of the brainstem. You guys cool with that? Okay. And it supplies the middle part of the brainstem with blood, and that is known as the basilar artery. So here I just kind of drew the pons, just to kind of show you that it's going up the brainstem. You guys go with that? Mm-hmm. Once you get up to the brainstem, it branches out into the superior cerebellar, okay? And then finally we're getting to, so basically here, at this point, okay, these arteries here are all cerebellum and brainstem, right? And once I get to the posterior cerebral artery, I'm no longer at the bottom of the brain, but rather I'm supplying blood to the cerebrum, which is the upper part of the brain, right? The cerebral cortex. You guys okay with that? And that gives me the posterior cerebral artery. And then you have this little U-shaped artery here. Do you guys see that there? Now this little U-shaped artery, I'm going to draw an arrow pointing in this direction and an arrow pointing in that direction. Blood can flow either way through this artery here. And this is known as the posterior communicating artery. Okay? So basically what happens is if I have a failure of one of my vertebral arteries, or both of them, blood flow to this part of the brain can come from the carotids, right? So blood flow, instead of coming from down up like normal, because of this the posterior communicating artery, blood can go from the top down and fill those areas. It's a backup mechanism. Does that make sense? Mm-hmm. All right. Now, the common carotid arteries, or the internal carotids, the internal carotid arteries, as they come in at the front here, and these structures here are the olfactory bulbs. So these are the nerves that go to your nose, right? Your olfactory nerve for smelling. So the nose would be right in here, just to kind of show you where those vessels are. So the internal carotids are coming in to the anterior part, and they branch into the middle cerebral arteries, and then they go out to the anterior cerebral arteries, and then you have a posterior communicating artery, and you also have an anterior communicating artery, which allows blood to flow either direction. And again, it's a backup mechanism. Okay? You guys cool with that? Okay. Now, I don't want you to spend all day and all night memorizing every single artery here. There are actually more than just this. Okay. But there are a few that I want you to focus on. All right. Because when you have a stroke and you have an occlusion of these vessels here, you will get different types of signs and symptoms, different types of strokes. Okay. And there are just a few really important ones. So there is a stroke that involves the posterior cerebral artery. That's this guy here. So if I have occlusion or compromise of the posterior cerebral artery, that supplies blood flow to the posterior part of the cerebrum, which is where? The occipital lobe. The posterior cerebral artery supplies blood here, so if I have a stroke that involves occlusion of the posterior cerebral artery, what primary signs and symptoms will I have?
Vision changes.
I'm going to have visual changes, right?
Yeah.
I'm going to have visual deficits. So this is going to hit my vision. You guys cool with that?
Mm-hmm.
All right. So that is a posterior cerebral artery if it takes a hit. All right. Now I'm going to move up to the middle cerebral artery, which is this guy right here, right? It's one of the major, two major arteries that comes off of the internal carotid, the middle cerebral. And it supplies, if you had to guess, the middle part of the cerebrum with blood. So right in here. So what is that primarily going to do? What is that primarily going to cause if I have a stroke there? Motor and sensory deficits. All right, motor and sensory deficits. And then finally, the anterior cerebral artery, which is here, which is the third major type of stroke syndrome. That's a compromise of these arteries here, the anterior cerebral arteries. You guys okay with that? And the anterior cerebral arteries supply blood flow basically to the top part here. Okay, so we've got the posterior cerebral, the middle cerebral, and then the anterior cerebral. So if you had to guess, the anterior cerebral is going to be primarily what? Primarily motor sensory as well. Okay, but this is the one where you see the real typical hemiparesis. What is that?
It's one side.
Like,
Or you realized on one side.
There you go, yeah. Right? Hemiparesis, yeah. Or hemiplegia, right? Paralysis or weakness to one side. You guys cool with that?
Yeah.
All right. So it does cause motor and sensory deficits, but the hemiparesis tends to be something that is a little more common to that. So hemiparesis along with motor and sensory deficits. You guys cool with that? And does that make sense? How cool is that? That, you know, we can actually make some sense of this. So this whole circulatory network that makes a circle basically around the brainstem at the base of the skull is known as the circle of Willis. And compromise to these vessels, okay, is where we get our major stroke syndromes from. Now, you also can get little aneurysms on these vessels. They're called Berry aneurysms in many cases. And when these aneurysms rupture, they can cause hemorrhage, okay? And so you can also have something known as a subarachnoid hemorrhage. And one of the most common causes of a subarachnoid hemorrhage is a rupture of an aneurysm where one or more of these vessels bifurcate, which obviously can be a very devastating injury, a very devastating problem in its own right. Okay, you guys cool with that?
Yeah.
Does that kind of make sense? Now, when we talk about motor and sensory information, okay, you have a motor and sensory cortex in the right hemisphere and a motor and sensory cortex in the left hemisphere, right? And in general, motor and sensory information, so if I have sensory information, okay, I touch this and it feels cold, right? So that information comes up, and where does it go? What hemisphere is that information going to come into? So I'm grabbing this in my right hand. Where's that information going to go to?
The right side.
The right side of my brain?
Or just press over.
Yeah, right, there's crossover. So sensory information is generally sensory information that comes in from the right gets processed on the left, and motor information comes out of the left and goes to the right, and vice versa. So in essence, the right side of the brain controls the left side of the body, the left side of the body controls the left side of the brain controls the right side of the body. There's that crossover of communication. Why do we have that crossover is very difficult to answer, and we don't have a real clear answer to that question. But there it is. So if you have hemiparesis on the right side, where is, in all likelihood, is that deficit? It is the left, right? So you're more than likely dealing with a left anterior cerebral arterial occlusion. Does that make sense? You guys cool with that? Okay, cool. All right, let's move on now. Whew, a lot of stuff there, huh? A lot of stuff. Okay, let's now move on talking about neurons, all right? The functional cell of the nervous system. So let's label some of the major structures of the neuron. This should be no new information really for you guys. It should be more or less review. Okay, so here I have a prototypical neuron, okay? So what are these projections right here that are coming out of the body? These are known as dendrites, okay? And dendrites are what receive information, right? So information comes into a neuron through a dendrite, right?
Yes.
What is this round part here where the dendrites come into?
The body of the.
And what was the name for body?
Soma.
The soma. This is called the soma or the body. All right. So this is the soma. Okay. What is this long structure here known as? That goes away from, it sends information away from. This is known as the axon, right? The axon. You guys cool with that? So I've got dendrites. Information comes into the soma via the dendrites. That information is processed in the soma, and then information is then sent out of the axon. You guys okay with that? Now there is a structure where the soma becomes the axon here, and this is known as the axon hillock. The hillock, okay? This is known as the axon hillock. There's a K in there. There we go. See K. All right. You guys cool with that? All right. So what I want to do is I want to talk a little bit about how neurons function. Okay? So the way neurons function is all or nothing. It's an all or nothing deal. A neuron either fires or it doesn't fire. Okay? Either fires or it doesn't fire. It either depolarizes or it doesn't. So what happens is, here in the soma, I have what's known as a resting potential. This is very much like the heart. And when I look at the membrane potential, is it more negative or more positive? More negative or more positive? It's just like the heart, guys. It's more negative, right? It's negative inside of the cell compared to outside, right? The inside of the neuron is negative, just like the inside of a myocardial cell. The potential across that membrane is negative. And I've drawn that in there, right? See, I have these little negatives here. So it's more negative inside and more positive outside, right? That's the resting potential, right? We say that the neuron is polarized. It's polarized. There's a polarity to it. There is a negative on one side and positive on the other side.
Yes.
That resting potential in a neuron is about negative 70 millivolts. Okay, so imagine that this is negative 70 millivolts down here, And then right here, I'm going to draw negative 55 millivolts. Negative 55 millivolts is about what the threshold is for the neuron. And just like a cardiac cell, what happens when you hit the threshold? What happens when you hit the threshold? Right, when you hit the threshold, those voltage-gated sodium channels open up, sodium rushes in, and the cell depolarizes, right?
Mhm.
That's where the all or nothing comes into play. If you cannot get that neuron to the threshold potential, if you cannot stimulate that neuron enough to get it to the resting what was I going to say? The threshold. Thanks. It's not going to depolarize, right? You guys cool with that?
Mhm.
That's where the all or nothing nature of this comes into play. So, what I'm going to do now is, let's say that this is a sensory neuron in my finger, and I'm going to apply some pressure, okay? And so just a tiny bit of pressure, and let's say a little bit of that pressure hits this little dendrite here, all right? And that dendrite opens up little sodium channels. There are little pressure-sensitive sodium channels. And so what that does is that allows a little bit of sodium to come into the cell, okay? So I stimulate that just a little bit, and a little bit of sodium comes into the cell, okay? So what I'm going to do is I'm going to draw this graph again. So I'm going to apply just a little bit of stimulation to this, right? Just a little bit. And what I'm going to see is I'm going to see a little bump up as sodium comes into the cell. You guys good with that? But is that enough to meet the threshold? Where's the threshold?
Above
No, it's not.
55. Negative 55 is the threshold, right? Did that bump get up to the threshold?
No,
So is the neuron going to depolarize?
no.
Nope. So now what I'm going to do is I'm going to apply just a little bit of pressure here on this dendrite here. And a little more sodium is going to come into the cell. And that's going to cause a little bump as well. Like that. Okay? And what happens is, if I add those two bumps together, it looks like that. That's the total amount of sodium. Has that met the threshold?
Yes.
Yes, it has. So what happens? The voltage-gated sodium channels here in the hillock open up, sodium rushes in, and the neuron depolarizes. Does that make sense?
So that's how you feel it.
Yeah, so that's how you feel it. Yeah.
Okay. So you have to reach enough pressure to
Right.
feel it.
Yeah. So you have to hit enough of these dendrites, okay?
Okay.
Yeah. Now,
We're so easy.
this is a concept known as temporal summation. It's a word you're going to want to know. It's known as temporal summation. It is the sum of all of the input over time.
No.
And if the sum of that input is enough to exceed the threshold, the neuron depolarizes. If it's not enough, the neuron doesn't depolarize. And here's the other part of this, guys. At the same time that these dendrites are being activated here, I could have dendrites being inhibited up here, okay? Maybe I gave some drug that is causing inhibitory action here. And so these dendrites here are causing negative charge to come in. And so that is going to push me toward or away from the threshold.
Away.
Away. And so really what the temporal summation is it is the sum of all of the positive input and negative input. And at the end of the day, if the positive input is enough to meet the threshold, the cell depolarizes, right? So you have positive and negative input coming in all at the same time, okay? And so you have this complex interplay. But at the end of the day, okay, the membrane potential has to be high enough to hit the threshold or it will depolarize. Are you guys, does that make sense? You guys cool with that? So this is how some of our drugs work. For example, if I give my patient a benzodiazepine, right, something like lorazepam, Ativan, midazolam, Versed, diazepam or Valium, right? Those medications work on a receptor for a certain neurotransmitter, okay, called a GABA receptor. And GABA receptors are chloride channels. Is chloride negative or positively charged?
Negative.
It's negatively charged. So if I open a bunch of chloride channels and I cause negative charge to enter the cell, chloride to enter the cell, is that going to push it toward or away from the threshold? It's going to push it more negative, right? So I might give somebody a benzodiazepine, okay, and let's say that their neuron, negative 70 millivolts, normally the neuron's resting potential is at negative 70, right? But let's say I give you a big dose of a benzodiazepine, and that causes those, that interacts with the GABA receptors and makes more chloride come into the cell, okay? And now maybe the potential is down here at negative 100 now because of that. I have hyperpolarized the neuron. So what does that mean when I've hyperpolarized it? Is it going to be more easily activated or less easily activated? Less easily. It's going to be harder to get that neuron to depolarize. And that is how benzodiazepines in particular cause central nervous system depression. They hyperpolarize the neurons and make it harder to depolarize the neuron. How cool is that? That just, to me, it's just amazing. It's just mind-blowing. It's like, wow, this is mind-blowing.
Literally.
Huh?
Yeah, literally.
Yeah, literally, right? Okay, so that's not the end of the story.
Uh-oh.
So, we have met the threshold. Voltage-gated sodium channels in the hillock have opened. Sodium is now rushing in, and this thing depolarizes, right? Now that signal needs to go somewhere. This neuron's like, hey, I just got some sensory information. I need to send that information to the brain, right? Let the brain know that my hand is getting burned off, right? That information has to travel from my finger all the way to my brain, right? Eventually, right? At some point it does, right? I mean, you do have reflexes where the information will just go to the spine and then you have that reflex. But eventually, you know, you've got like, oh, I just burned my hand off. How unfortunate, right? There is some higher order processing that occurs. So for that information to get to the spinal cord or the brain, it has to travel a long distance, right? You guys cool with that? So what happens is, that wave of depolarization, all those sodium ions, as they rush in through those voltage-gated sodium channels, they're going to rush into the cell, and then like charges attract or repel.
Repel.
Like charges repel, right? They want to. So the sodium wants to get away from itself, and so what happens is it starts getting pushed, right, away from itself down the axon. You guys cool with that? But here's the problem. This signal needs to get to where it's going, and it needs to get there. And the signal needs to be strong enough. There needs to be enough sodium that when that signal finally gets down here into the axon terminal, it can cause channels to open in the axon terminal, right? Because if that, otherwise, neurotransmitters won't get released. So, what are some things that we need to do to make sure that that signal is strong enough when it gets down here to cause something to happen? Well, let me ask you guys this question. Let's say I want to charge my computer. I want to charge my computer, and I'm going to plug a piece of copper wire into the outlet there, and I'm going to run that copper wire into the computer here. Just the wire by itself. Is that going to work?
Probably, maybe.
Why might it not? Why are you guys uncertain as to whether it'll work or not?
Something has to regulate.
Okay. Might be.
protecting it, also increasing its,
Yeah, the gaps.
There you go. Can I steal this?
Yeah, you can.
Okay. You guys see this, right?
yeah.
So I have a wire in here, and that wire is metallic, and it has low resistance. So low resistance allows charged, right, electrons. That's what's going through this wire is electrons. That's what electricity is, electrons. And electrons are just negatively charged, right? So there's charge moving through this wire. And the less resistance there is, the easier it is for that charge to move through, right?
Mm-hmm.
So that's one thing. I need to have a wire, i.e. an axon, that allows charge to move through it. But the problem is, if I just had a wire all by itself, could some of that charge leak out into the environment? Yeah, right? And so that signal, as it traveled from the outlet to her computer, it would get weaker and weaker as it got there because it would leak out, right? So what I need to do is I need to surround that wire in an insulator that has high resistance to prevent that signal, that charge from leaking out, right? You guys cool with that? But is there something different about the way that this wire is insulated versus how your neurons are insulated?
Yeah,
What is that difference?
there's gaps in
There are little gaps called nodes of Ranvier. Nodes of Ranvier. I hear some people have even called them nodes of Rainier, but I think it's Ranvier. I'm not.
There's a V in there.
Yeah, I'm pretty sure there's a V in there. I was actually fluent in French in high school. Yeah, not anymore. Huh? Yeah, I don't speak it anymore. Yeah.
It's a terpene.
It is a V.
Sounds like a.
I thought it would be good for hitting on people. French. Didn't work. Anyway, why is that? What's going on there?
Because you can speed up the impulse,
Well,
or it has less resistance there.
no, it just not resistance. Here's actually what happens. So, what happens is as these sodium ions travel through the axon, they become spread out. They spread out, right? And they become less and less dense because they're really packed here, right? The signal's really strong here, and then as it spreads out, the sodium ions kind of get spread out and the signal gets weaker and weaker and weaker, right? Does that make sense? And what happens is, if I didn't have these nodes here, that signal would be so spread out and so weak by the time it got here to the axon terminal that it wouldn't be able to activate these channels here. So what happens is every so often I have a node and I have more sodium channels at those nodes, and those sodium channels allow more sodium to enter. Okay, so the signal gets amplified here and then it moves out, it spreads out, right? Spreads out, it gets weaker and weaker until it gets to the next node, and then it gets amplified again until it gets to where it needs to go. Does that make sense? So it gets amplified, it gets weak, it gets amplified, and it's a kind of, if you want to think of it, it's a kind of jumping or skipping motion, where the signal kind of jumps from node to node to node, and that term is known as saltatory conduction. Okay, it's known as saltatory conduction. Saltatory conduction. You guys cool with that? That makes sense?
Yeah.
All right. All right, so we've got there. Finally, the signal gets to the axon terminal, the end of the axon, and there are some other channels in the axon terminal. They're not sodium channels, though. These channels are calcium channels, Ca+2. So once that signal makes its way down to the axon terminal, That signal causes these voltage-gated calcium channels to open up. Calcium enters the cell, and calcium interacts with little vesicles in the axon. And these vesicles contain neurotransmitter molecules. And calcium allows the vesicles to leave the neuron, and when they leave, they dump their neurotransmitters out here. Okay? And where the axon of one neuron interacts with the dendrite of another neuron or some other tissue, we call that a what? Yes?
Synapse.
A synapse. And there's a special term for the synapse at muscle tissue, which is known as the neuromuscular junction or the in-motor plate. Okay? All right? Those neurotransmitter molecules are released into the synapse, and then those molecules interact with receptors in the dendrites of another neuron or on other types of tissue. And these neurotransmitter molecules can either cause excitation or inhibition. Okay? And it can either cause another depolarization or it can prevent a depolarization from occurring. And then that occurs again and again and again, and you have 100 million neurons doing this constantly. Off and on, inhibition, excitation, etc., etc., etc. You have this complicated mess of stuff going on. Are you guys cool with that? Does that make sense? How a neuron receives a signal, how the signal is processed, how it propagates through the axon, how the neurotransmitter really is released, and how it leaves. Are you guys okay with that?
Yeah.
So a neurotransmitter is a way of turning an electrical signal into a chemical signal, an electrochemical signal. Are you guys cool with that?
Yeah.
Make sense? Okay? So far, so good?
Mm-hmm.
All right. I'm going to talk a little bit about just a couple of different types of neurons. There are some different types of neurons. Okay. There is a type of neuron where it's just the cell body and the axon, just like that. And that's known as a unipolar neuron.
I see where you're going.
Yeah, unipolar. All right. And then we have something called where you have your cell body, your axon, and then you have dendrites. Kind of looks like this one here, huh?
Mm-hmm.
Probably looks like most of the neurons that are drawn in your book.
Mm-hmm.
What do you suppose this is called?
Multipolar?
Or bipolar?
Polypolar.
Yeah.
Pseudopolar?
Multipolar.
Unipolar?
Yeah, multipolar. You guys okay with that?
Yeah.
All right. And then if I just have one dendrite, a cell body, and an axon, that is called bipolar. Unipolar is just cell body and axon.
What about the pseudo-unipolar?
And you do have what's called a pseudo-unipolar as well, which looks like this. It's just an axon that goes to a cell body kind of off on the side like that. Like that. That is known as a pseudo-unipolar. For the most part, most of the neurons in the body tend to be multipolar. Okay, so that's why I put this drawing up here, because most of them are multipolar. Specialized motor and sensory neurons can have different structure. Bipolar, for example, your optic nerve, light comes in and hits just one dendrite, and then that light is transformed into a nervous signal that goes to the brain. So your optic nerve would be an example of bipolar neuron, which is special sense. Hearing as well, okay? And then pseudo-unipolar is something that is a neuron that's really important in sensory information, which we'll talk about here in just a little bit. But are you guys okay so far?
Mm-hmm.
It's a lot of information, I'm sorry. It's not gonna get any better. There's more coming. And then more. Let's see, what is it, was it 11?
11:05.
Yeah, I'm gonna be lecturing a little later than normal. I'm gonna lecture till probably noon. All right, get out of here. Take 10 minutes, guys. 10 minutos más.